Okay, so we want K such that the linear system is consistent. All right, so basically, again, we're looking for a solution. Um, it's a question of dependent, independent, that's irrelevant. It's just we need a solution to exist. All right, so we have something in standard form. K is our coefficient, so we'll create a matrix from this. 9K, 9K, 1, -3. All right. If there's a way to do this in the calculator, I don't know. So we go right to doing it by hand. We want to get it in a reduced row echelon form. So one thing to keep in mind, again, is along the main diagonals, we want to have ones, ideally. Anything below the main diagonal should be 0. Right? If we want to reduce row echelon form, then your pivot values should be the only non-zero values in any column. Right? All that basically means is, let's try to row reduce this, so I want to get rid of that K. And if I can, I also want to get rid of that K. All right? So let's do that. All right, so if the K is going to go away, I need to divide out a K. So I got to take row 1. I want to basically make this 9 first into a 1. And then use that, or I guess you can make it into a K, a negative K. In order to do that, I'd have to multiply it by negative K over 9. All right, so that's going to make this 9 go to a 1, and we'll have a negative K left over. So if I add that result to row 2, nine K9, 0. A little bit more complicated here. This is going to be negative K squared over 9 plus 1. That's exciting. To row 2, yep. So negative K squared over 9 plus 1. Now the other guy, well, this is the same kind as that number, so this is going to become a negative K. Negative K plus negative 3, so negative K minus 3. All right. So we have zeros below, or 0 below the main diagonal. So we are in echelon form. It's a question of, do we want to get into reduced echelon form? Also, I want to just make sure that the last entry in row 2 is not the pivot value. So I just need to come up with a value of K that allows this number to exist. So if I can do that, I pretty much have it. Right? But if you want to go further, you can. I mean, I can divide out a 9 in row 1. I don't think it's going to advance the plot, but I'll do it just to make it look a little nicer. So that would be 1, K over 9, 1, and then all this stuff. I could also try to make this into a 1, but there's a few different ways to go at this point. But if you want to just cut right to the chase, I understand that. This, we want this to exist. This needs to be unequal to 0. Okay, which would make it the pivot value, the first non-zero value in this row. Right? So as long as they come up with a k value that'll keep that from being equal to 0, I think they'll be in good shape. Right? It doesn't really matter what this is if that one is unequal to 0. If this one is equal to 0, then I need this one to also be equal to 0. Right? So that's another condition. So with that in mind, you may want to continue the process. So to get it 0, 1, so then all you have to worry about, not even really worry about it, it's just come up with the values of k for the last entry. But I already started writing this, so I'll continue. So negative k squared over 9 plus 1. I'm going to set that equal to 0 and solve. All right, so when I set it equal to 0, I get k equals plus or minus 3. All right, so we just want to play that out logically. Because these might be okay values. Again, I don't want this to be equal to 0 unless this is also equal to 0. That's the key ingredient here. If this is unequal to 0, we're good. If it's equal to 0, that must also be equal to 0. All right, so let's take a look at that.
Why did that get equal to 0? Because it would be like, would make sense.
If this one is equal to 0,
yeah.
Then it could make this the pivot value. And if the pivot value is the last column, then it's not a solution. Okay, so let's just, we could just plug it in and take a look. I don't like that one. So 1, let's focus on a 3. I'll write 3/9. 1, 0. If I plug in the 3, I'm going to get 0, which would be a bad value, right? If this one is not also 0. So when I plug in the 3 here, I get negative 9 over 9, which is negative 1, plus 1 is 0. So let me see what happens. So I'll just make a note. If this is k is equal to 3. If I plug in a 3 here, I get negative 6. All right? That would be an inconsistent solution. Inconsistent system. And again, that's because the pivot is in the last column. So let's take a look at k equals negative 3. All right, so if I put in a negative 3, I get 1. So the top row is irrelevant, but I'll write it anyway. Negative 3/9, so negative 1/3 if you want. 1, we still get it, oh, not 1, 0. I don't know why I wrote a 1. If I plug in a negative 3, I also get a 0. If I plug in a negative 3 in the last column, though, I get negative 3, which is 3 minus 3 is 0. All right, this is consistent. All right, so we just have to kind of formalize this and come up with an actual final answer. But the only values of k that were concerning were 3 and negative 3, because everything else that I would put in for k here would allow that entry to be a non-zero value. If this is a non-zero number, we're good, because non-zero would mean that the pivot is before the last column, which would give us a consistent solution. All right, so out of the 2 that we were concerned about, the only one that led to an inconsistent system was the value 3. So if I'm looking for values of k, really I'm just saying k belongs to the set of real numbers such that k is not equal to, what do they say, 3? I mean, you could write it any way you want. You don't have to use any kind of notation. Just say anything but 3. Now, if you really want to cross the T's and dot the I's, then get this down into reduced row echelon form, and then go from there. But I don't see that being necessary, because once you get it into echelon form, you know, algebraically we get the same thing done with echelon form that we do with reduced echelon form. All right. What else?
You have to leave A, B, and C in your matrix when you do it.
You're gonna be left with A, B, and C, right?
Yeah, I think so. Yeah.
The answers be like whatever you give like the operations, you're gonna find A, B, and C.
Yeah. I just want to see if there's any kind of shortcut to that. I mean, one thing that you could try, just, you know, sort of roll the dice on this, would be, you know, don't put the augmented matrix in, just put in the, my brain's not working right now. Why can I not? Well, it's a square matrix, but I'm blanking on what the word is for the non-augmented form. All right, so you could start with this, but there is a drawback to approaching it this way. The drawback is it could be a complete and total waste of your time. Pretty significant drawback. Yeah, complete and total waste of your time. All right, the reason I say that, I don't know, hopefully you already know why, but just in case, it's this last row that's the problem. Because if I need this to be consistent, what I need is for the last entry to also be equal to 0. Right? Because if your pivot value is in the last column, it's not a consistent solution. Right? So I actually need to know what transpired to make this row here all zeros, which means I actually have to carry out the row reduction. Although, I mean, you get some value out of it. Like, off the bat, I know I don't have to mess with row 1. There's something there, I guess. Yeah, I think the reason why I say it's a waste of your time is because the only situation in which this would work would be if you got a solution, you know, you got non-zero rows at some point in your matrix. So very rare. You can't expect that to be the case. It doesn't seem like it would be much of a question if it were. So I suppose I can just do this. I would then be, let's see, negative 2R3 plus R2, G2. 0, 3, 3, then the fun one, negative 2C plus B. Then I would do 1/3 of row 2. Yeah, that wasn't like a moment of inspiration or anything. That was just me looking down and seeing what I was supposed to get. 0, 3, 3 is supposed to become 0, 1, 1, so multiply by 1/3. I think we're almost there. We could make this 0 out, but I don't really want to do that. If I add them together, oh, I'll get 1, 0, 2. Yeah, right. So row 2 plus row 3. So you'd really be adding 3c over 3. So 3c minus 2c is c, so it's actually c plus b over 3. Surprisingly nice. Then negate row 1, add to row 3. That's actually the last step, right? Yeah, so I'm just going to do it this way. So c plus b minus a over 3. All right, and so I just need to, answer would be in terms of a, b, and c. All right. Really? Yeah, I guess so. Yeah, so I just need that quantity to be equal to 0. So c plus b minus a over 3 needs to be equal to 0. Otherwise, there'll be a pivot in the last column, which I don't want. Cross multiply, I get c plus b minus a equals 0. So anything that satisfies this equation would give us a consistent system.
E says like minus 3a plus b plus c. Is that okay? It was like same thing or no?
I don't think the A is.
Wait, I had negative 3a plus b plus c.
So you derive this answer with that?
Yeah.
C plus B minus A.
Yeah, just sort of, one of these two.
Okay.
This needs to be equal to 0. Otherwise, there's a pivot value in the last column. Well, I either made a mistake then or now. So I'll have to look at that.
Your A isn't supposed to be in that numerator because you're subtracting it, but it's not over 3. So the green is not.
Schnitzing grouping. Yeah, okay, so with a common denominator, it would be minus 3a. I had the a, I was missing the coefficient. Yeah. That was weird. Just kind of threw it in. Yeah, this should be 3a over 3. So there it is.
Is it possible to like do that but get a different row too, but still get the same answer?
I think so.
Okay. Because like my row 2 was negative 2a plus b, but then my last pivot point in row 3 was negative 3a plus b plus c.
So at some point you must have done a row 1, row 2 interaction.
Yeah, well, the first thing I did was negative R1 plus R3.
Oh, negative R1 plus R3. All right, so that brought the A down to the C. Oh, and then at some point you must have done R2, R3?
Yeah.
Okay, that brought the A into the R2.
Okay, but it's okay if I
Yeah.
click C.
Mm-hmm. Man, typo. Reduce echelon. So for these, we're just making a determination of whether they're in row reduced form. Some cases easier than others. In the first case, we're looking at R2 and R3 being out of whack. So not. The second one, let's see, pivot values look good. Zeros below the main diagonal, true. Pivot values are the only non-zero value in the given row. Sorry, given column. True, true, true. All right, so these are the 3 columns that we're concerned with. 2 is not a pivot value because it's not the first non-zero entry, so we're not worried about that. It looks good. So, yep. The last one, all right, pivots look good as being the first entry, although this one would not have a solution if it were a system because the pivot's in the last column, but that's not what they're asking. All right, so the first 2 pivot values are fine. The last one is not the only non-zero entry in its column, so not. I don't. This is one where I didn't have an answer key up. I don't think. So might as well just do it. The graphical determination is based on you plotting the original vectors and then working off of those. So we have UVW111. That's easy enough. Let me just get a 3-dimensional coordinate system. All right, so 1, 1, 1. So we want to create a parallelogram for x and y. 1 in the x direction, 1 in the y direction. Create a parallelogram to give you the base of your coordinate. All right, let me label this x. Well, I'll just do x, y, z. x1, x2, x3, x, y, z, it doesn't matter. Now we want to shoot up 1 unit. So estimate, you can use it in the side of your index card if you want. You could just ballpark it. But basically, I'm just taking this distance and using this vertex here and that same distance to come up with my coordinate. All right, so it's going to be right about, yeah. And then draw an arrow to it. So that's our U. I'm just going to attempt to color code it anyway. All right, now you could start plotting the other points if you want, but you could also kind of work as you go here because I eventually need 2 U's, so why not just plot it now? So take this distance and double it. All right, so all I did was I just stacked it on top of itself. 0, 2, 0 is very easy to plot because that's right on the y-axis. 2 units. Looking at something like that. 0 in x, 0 in z, but 2 in the direction of y. right? So I have to do matrix, oh, not matrix, vector addition here. 2u plus negative v. All right. So 2u negative v. So let me grab negative v real quick. That's just same distance, just going in the opposite direction. So here's my 2u, here's my negative v. I want to create a parallelogram out of that. So I'm going to move this up, I'm going to move this over, and then draw my resultant vector. All right. The key here is just keeping track of everything. But all of this stuff here is that blue line. That's what vector. So I don't have to worry about the first part of my expression anymore. That's all embodied in that one vector. All right. Now W, 1, I think that's the one that got cut off. 1, negative 1, negative 2. All right. So 1 in the direction of X, negative 1 in the direction of Y, and then 2 units down. All right. So it's going to get real messy real quick, I guess. So that green angle there, that's the parallelogram that I'm creating by going 1 in the direction of X and 1 in the direction of negative Y. Now I just need to go 2 units down. So here's 1 unit for Z. I need double that, so I can ballpark this and then estimate it on the graph. So it's going to be right around here. All right, so that's my W coordinate. I want that to be a vector, so connect it to the origin, throw an arrow on it. All right. So these two, well, not yet. I need half of that because it's half of W. So I can get, that's easy enough. Here's my relevant vector. So my vector sum is going to be related to the blue and the orange. So this is very messy now. All right, so create a parallelogram out of that. So bring it down, bring it over. Actually, it looks like it's going to be pretty close to being along the negative y-axis. Right, so let me just do something. I think I can just kind of clean it up a little bit. That I think I need. Nope, too much. All right, a little bit better. So this guy, no, off at the wrong angle there. Looks a little too much like the negative y-axis, but it's the best I can do. All right, so So that vector is the answer. Time. Yeah.
Can you just go first?
Sure. It becomes a disaster. Yeah, yeah, just enough for me to know what you did.
So would you do like 2u negative e and 1/2
I think
u
so.
and then put them together?
Yeah, I think
Instead of doing like u, then 2u.
right. Yeah, if you got to cut out the middle steps, that's fine.
Okay, and then do you also need to do all the like parallelograms?
No, no, if you can get them without the parallelogram. Because I only do that so I have something to point to, but really when I do it on my own, it's like, all right, this, that, plot a point, draw a line, you know, like that's pretty much how it should be. Number 7, you said. All right, so we have to solve the system and then write it in parametric form. So directions are important, obviously. If it doesn't say to do something by hand, then I wouldn't do it by hand. 3 by 6. All right, so user interface issues. That could be a problem, but hopefully not. So just double check. Make sure. All right. So good. All right. So we have, well, I mean, part A is really kind of like the embodiment of parts B, C, and D. Because I don't see how you're getting the solution without doing everything else, or at least having a sense of everything else. So, but I'll write it all out anyway. So we have x1 minus 4x5 equals negative 11. x2 minus 8x5 equals negative 18. Right?
Calculates 3 by 6, but it's 3 by 5 when the calculator gives you
You just cut off
edge cut off. Okay.
Yeah. Quick double check a Rooski here. Looks good. So x1, oh, that's too dark. Equals negative 11 plus 4x sub 5. x2 is equal to negative 18 plus 8x sub 5. X sub 3 is 2 minus x sub 4 minus 3x sub 5. which implies that x sub 4 and x sub 5 are both free. All right, so x sub 1, 2, 3, 4, and 5. All right, think about what we have and what we need. So I need a vector for my constants. I need a vector for the coefficients of x4 and a vector for my coefficients of x5. So my constants, I only have constants, notable constants for x1, 2, and 3. So implied constants of 0 for x4, x5. All right, so we're looking at negative 11, negative 18, 2, 0, 0. Plus we have our x sub 4. Coefficient of 0, 0, 1, 1, 0. Negative 1. Zero, zero, negative 1, 1, 0. And then x sub 5. We have a 4. We have an 8. We have a negative 3. We have a 0. And we have a 1. All right. So we need the particular solution P and the VH. So let's say you're in the middle of the test and you knew what all that stuff was the day before, but for some reason it's just not there. Worst case scenario, I mean, you do have a calculator. Find the homogeneous solution, which is to say the matrix without the B component. All right, so you just knock that right out. All right, so just make your B vector equal to 0. And then look at what you have. All right, so basically, I mean, really, if we just kind of cut down to the chase here, you compare what you have here in this reduced row echelon form to what came before it. And you can see that the obvious thing that's missing is the column containing the negative 11, negative 18, and the 2. Okay, so what that means is that this must be particular to that equation. Everything else must be the homogeneous component. All right, so P V sub H. And again, you're only doing that if you forgot the relationship. The particular solution is actually, I mean, when you think about it, it's the one that's particular. It's the one that's not in general terms. These are dependent on x4, x5. The particular one should be constant. It should be a numerical vector. So find the one that doesn't have variables in it, and that'll be your P. Everything else is your V sub H. Is good. Linearly independent. We talked about that earlier. That should be gimmies. Again, you're just looking for whether or not they have a trivial solution. So put this in your calculator. Solve. You got to have a 0 column, right? Because you're setting it up as a homogeneous system. So that additional, you can work with this without the 0 column if you want, but I tend to throw it in because I mentioned it before. That's the kind of thing I would forget. I get an answer and I'd be like, oh, it's non-trivial, or it's trivial because I just neglected the fact that there is a column of zeros. Right? So I'll do 8A, I guess. Do an easy one. Oh, no. So this would be a 2 by 4. negative 2, 0, 0, 4, 5, 0, 0. All right, so just give me the row reduced matrix and then go from there. All right, so here we're looking at only the trivial solution. Therefore, it's independent. So, I mean, you could write it, I mean, this would be x1 equals 0, x2 equals 0. But the idea is that you don't have other constants within your reduced matrix that would cause there to be dependence. Right? Because I mentioned it before, independent is real, I mean, it's not as definable, I would say, as dependent. Dependent is very, very defined because you look at x3 here, for example, and if you're asking, is it a dependent solution? Well, does x3 depend on anything? Yeah, it depends on what x4 and x5 are. So it's dependent. If it doesn't depend on anything, then it's not dependent. So
you could want like your error equals 0 if it's true.
correct. All of them. The clockwise rotation one, again, you know, while I'm in a groove here, we're only working in 2 space, so we add the j component at 0, 1, the I component 1, 0. I want to move those in a 90-degree fashion. So I becomes 0, negative 1. J is going to where I is. So my transformation vector here, just think, where's I going? I is going from 1, 0 to 0, negative 1. J is going from 0, 1 to 1, 0. So that's my transformation vector that will do the 90-degree rotation in the clockwise direction. So carry out that process. So 1 multiplied by 0, negative 1, plus 2 multiplied by 1, 0. All right, so that's the first transformation. The second one has us reflecting over the line y equals negative x. All right, so yeah, maybe you're a little iffy on your transformations. Worst case scenario, just go back to, like, I think it was algebra 1, maybe algebra 2, and just play around with stuff. All right, so you have the line y equals negative x. That's this line here. I want to flip over that line. So let's say I had the point 1, 2. Or it doesn't matter what the point is, any point. If I were to flip it over that line, I'd be looking at the straight line distance between the point and the line, and then I would want to go the same distance in the opposite direction. All right, so looking at something like, well, that looks terrible. So something like that. It's got to be over here in this neighborhood somewhere. So it's a question of how do I get there? All right, well, when we flip over the line y equals x, we just switch the x and the y. If you flip over the line y equals negative x, it sounds like it's kind of the same idea. So if we switch the x with the y, we would get 2, 1. That would put us over here. Okay, so that's not it. But if I then flip it over the y-axis, because that's what happens when you negate x, that sounds like it would get the job done. All right, so we have 1, 2, -2, -1. Sorry, -2, +1. All right, so now we just got to put that in the form of a transformation matrix. All right, so, but at least we have a sense of what the end game is supposed to be. All right, heartburn. So, again, we switched x and y, and then we negate x. All right, but we could also do the same thing with the component vectors I and j. Because again, ultimately, to come up with your transformation matrix, you want to be thinking about, well, where are these things going to end up?
If your right side of the y-axis, the original point, should be on the bottom side of the x-axis for the second point, reflecting.
Well, I was thinking right side of the y-axis puts you in positive x's. So if you flip, wouldn't you be above?
Well, if you like,
Oh, distance. Yeah, maybe you're right. I see what you're saying. Because it's this distance plus a little bit more, so it would be this distance plus a little bit. Yeah. I think I tried to make my coordinate jive with my picture, but my picture was fundamentally flawed because I'm a fundamentally flawed artiste. Yeah, I still can't do it, even when I have help. So it should be like that. L to replay. -2, -1, y equals -x. Yeah, something feels wrong. Because
like if you were to take like a cylinder,
if you what?
if you were to rotate it like as a cylinder, and then figure what you're going, you still have the same distance.
Right.
So
Yeah, I get it. Maybe my coordinates or my picture is so terrible.
I think with the line you put at too much of an angle, so it kind of.
Yeah. Yeah, something just wasn't visually playing out the way I want. All right, so let me just 1, 2. Let me do Oh, why did it select plane? Dumas. Ah, son of a gun hack. There we go. Okay. And then reflect. A over F. There we go. A halfway decent picture anyway. Rid of this garbage. Oh no! Why nay? Alright. It's weird. I don't know why 270 gave me that other angle. That other point. Oh wait. The rotation's happening first. So then I want to do why is it top A. Okay. And then reflect A prime around or over F. Okay. Actually, I'll just take this picture. Okay, so anyway, what we're getting, so that took way longer than it should have. The reflection part, 1001 is going to 0, -1, -1, 0. Because we're switching and negating. So, just now, I'm still not in love with this. I don't see how that's going to end up being a decimal. So we would be doing 0, -1, -1, 0, multiplied by 2, -1. So 1, -2. That doesn't look like that, though. I think GeoGebra is letting me down here. Because the rotation should have been clean. But it gave a decimal. Around 0, maybe? No, there's something wrong with the rotation. You have failed me, GeoGebra, for the last time. I gotta figure it out. I wonder if it's... Nah, it can't be in radians. Can it actually, can it be that simple? I already know. I already know the answer to my question. Yeah, of course. Whatever. It's the little things in life. 1, -2, that's what we said. And that's what they say. Alright, so that was fun. Alright, the number 10 we kind of did. Sort of, today. Can puzzle if you want another look at that. Got your gimmies. Love the gimmies. I always look for the small sums to get started, or the large differences, because those kind of narrow themselves down. And then from there, you kind of work out what can and cannot happen. Like, for example, the 4 plus, I know it can't be 2 and 2 because it can't repeat within any row or column. So I know that that has to be 1 and 3 in some order. So I'll just make little notes. I know this has to be 1 or 2. Now this is a 5x5 puzzle, so I can work with the numbers 1, 2, 3, 4, or 5. What I get from this is that I know that this one can't be a 5 because there's nothing to pair a 5 with in order to get a quotient of 2. One of these has to be a 5 because how else are you going to get to a product of 60? So 5 times 12 gives me 60, so I just got to get to a 12. So 3 and 4 is what's going to happen. So I know that if I'm dealing with 3, 4, and 5 as my possibilities, yeah, I'll just make the note here. It can't be the 3 because I'm using the 3 in some fashion here or here. Now, if I know one of these two entries has to be a 5, then this one can't be a 5. So I'm able to draw a conclusion here, and that this has to be a 4. All right, so we're dealing with 2 and 5 left over. You too. So that has to be the 5 because, again, we're not getting to a quotient of 2 utilizing a 5. So if this is a 5, then that has to, in order to give us a difference of 2, has to be a 3. All right. This has to be 2 or 4 in some order, but I know that because I'm using the 2 here, that it has to be the 4. And that would put the 2 there. All right. So 3 and 5 in the upper right-hand corner. I haven't narrowed down which is which, at least yet. In a second I will, because this has to be 5 and 2 in some order. I know it can't be 3 or 4. I mean, normally it could be, but I already used a 4. So I can't have a 3 or 4 here. So if I know one of these is a 5, that one can't be the 5, making it the 3. Making this the 5. Alright, so it's the little things. like for example, the 4, I said look for large differences. 4 with a minus can only be one possibility, 1 or a 5, a 1 and a 5 in some order. But I've already established where the 1 is and where the 5 is. So this has to be the 5, that has to be the 1. Process of elimination, this is the 3. 3 could go with a 2 or a 4. I haven't really narrowed down which is which, but I do know that because this is a 1, this can't be a 1, making it a 2. Making this the 1, a 3, a 1. Process of elimination, this is now a 4. This has to be a 5 here with a 2 there because I already used the 5 up here. All right. Normally I would say 3 and 4, but I already used the 3 and 4. All right. Possibilities left over are 2 and 4 here. And 3 or 4 here. Already used the 3, so this is a 4. 3. Because this is a 4, this is a 2. Making that the 4. Because this is a 2, this is a 5. Making that a 2. And you just do a quick double check, make sure you can repeat the any row or columns, and you're good to go. All right. Was there anything else from the review that you wanted me to go over? Six? Okay, so we want to know whether it's in the span. Span of S in R3. So we want to establish whether or not we can have a linear combination of vectors 1, 2, 3. So the vector I, because it's in 3 space, is 1, 0, 0. So we're looking at 1, 0, 0. And you could actually write it as a linear combination first, you know, establish the weights x1, v1, x2, v2. I don't think you need to do that. I mean, I know you don't need to do that. The vector 2, cosine and sine of 45, we talked about this, is rad 2 over 2. Negative rad 2 over 2. Positive rad 2 over 2. 1. Now we want to know whether or not this spans R3. So it's like, well, all right, well, what's R3? Well, any point in R3, which we would designate with A, B, and C. Or something else and something else. So you just need dummy variables in there. All right. So we want to row reduce this. Calculator can be helpful when it comes to this sort of thing. But we went over something similar where it's only in the rarest of circumstances where the calculator is going to do all the work for you in this, because generally we need to know what's happening among A, B, and C in order to get a solution. Right? So, long story short, you're better off just doing it. Let's see. If I add row 2 to row 1, that'll cancel out this guy. If I subtract, it'll cancel out that guy and double that guy. So really it's one way or the other. So let's see, what do I want to do? I will just add them. R2 plus R1. So 1, we're going to get a root 2, a 0, and an A plus B. Don't forget, scalar multiples are a thing. The most commonly forgotten part of the triumvirate. Multiply R2 by root 2 over root 2. And it's going to kind of funkify your b variable, but it's going to make everything else into ones. Now, fun fact. Two divided by root 2. I mean, it's 2 to the first power over 2 to the 1/2 power. This is the same as root 2. So if you wanted to do like a little housekeeping step, you can make it 1 root 2 0 a plus b 0 1 1 b root 2 and then 0 1 1 c. All right, that's a preference thing. It's up to you if you want to do that. It might be worth it just to keep the algebra a little simpler. Okay. So now I can take my negative root 2 or negative r2 and add to it r3. 1 root 2 0 a plus b 0 1 1 b root 2 0 0 0 c minus b root 2. All right, now it's in echelon form. It's not in reduced row echelon. Well, actually, I think it is. Is it? No. Oh, I gotta get rid of that. Yeah, you're like a step away. If you multiply by negative root 2 on row 2 and add to row 1, then I think it'll be it. So 1, 0, negative root 2. Then when I take the negative root 2 and multiply it by b root 2, that gives me a negative 2b plus a plus b, so a minus b. But the bottom line is that wasn't really a necessary step, because we need to make a determination of whether or not this is going to, we're going to be able to span, whether or not S will span R3. The only way that that's going to happen is if you have solutions that always exist. Here we're looking at a situation where it's actually only going to exist under one particular set of circumstances. Right? So solution only exists if c minus b root 2 is equal to 0. Or you could say c is equal to b root 2 or whatever. So that's a dependent situation. So we're basically saying that it's not going to exist under all circumstances. Because it doesn't exist under all circumstances, then we can't say that S spans all of R3. All right? All right? So it must be a solution that always exists, right? Which would mean that if your pivot value occurs prior to the last column, you're guaranteed to have a solution. Right? Because our pivot value is in the last column, it's not going to play out. Right? And that's good news, because what that means is that, you know, if you're looking for the case where it does not span, then you really only have to focus on the non-augmented matrix, just to see if there's a pivot value, right? Because if there is, if we want to see that it does span, if the pivot value occurs prior to the last column. So when you do row reduction on the 3x3 matrix, if you have a pivot value in each of the first 3 rows, each of the first 3 columns, then you're showing something exists in all situations. A solution exists. But by showing that there are zeros, that indicates that it would not be a span. Right? It would not span all of R3. It only actually spans when C minus B root 2 is equal to 0. So.
If you had like one right before C minus B, then you would say it spans all.
Yep.
So do we need to show the ABCs, or can we just put that into the calculator?
In this particular question, you could go to the calculator route. You wouldn't need the A, B's, and C's. But if let's say I rephrase the question to something along the lines of determine a relationship between A, B, and C that allows for a consistent solution, consistent system, then you need it, right? But the way this one is phrased, you could go right to the calculator. Yeah. All right. Anything else? Let us know. I think.